All right, so quadratic word problems. A little blurb there. Sources from ancient times. Most extensively, the documents from the ancient Babylonians and Chinese times contained rhetorical problems, which could be translated into quadratic equations. These real life, mostly geometric problems, very much gave rise to the many quadratic formulas that we see today. All right, so the examples that you see here, you have different forms. You could see form one, sum and product of two unknowns. We could use either the Babylonian method or a modern method to handle those kind of problems. Right? So, such word problems are translated x plus y equals a and x y equals b, where x and y are two unknown variables and a and b are constants. Right? So, we can do this using the Babylonian method, which is the difference of squares. It makes use of this property c squared minus a squared is equal to c plus a, c minus a, where c is a divided by 2, right? Making c plus a and c minus a are factors of the equation. Right? The modern method involves substitution, right? So plugging one function into the other or one equation into the other and simplifying. If you factor the quadratic equation in that form, you'd follow these steps, find two numbers whose sum is b, the coefficient of middle term, and the product is c, which is the constant. Rewrite the equation in factor form and then set each factor equal to 0. It's called the zero product property, right? And of all of this seems like it's like, what are we even talking about? You'll see when we get to actual numerical examples, it'll make more sense, right? You could also have area problems, area of a rectangle, area of a square. And for that, you could use the Babylonian completing the square method. You could also use, if you wanted to use Babylonian quadratic formula, you could do that too, because that's just an extension of the completing the square approach, right? So find two numbers that have a sum of 30 and a product of 104, right? So we would figure out half of the sum and then use that to come up with the two factors, and then that would be multiplied to equal 104, right? And then we would solve that out, right, using distributive property and solve for x, right? So I'll just kind of, maybe I'll just use this example. So the sum is equal to 30 and the product is equal to 104. All right. So I'm making sure I write it down right. So the first thing, that first step is to divide the whatever that sum is by 2. Right? That's what we're looking for there. So divide the sum by 2. 30 divided by 2 is going to be equal to 15. All right. And I'll do another example after this in a sec. I just want to make sure I have one that's ready to go. But I have that value, which is going to be written as, or two factors, 15 plus x and 15 minus x, is going to be multiplied to equal 104. All right. And the rationale behind this is if the two numbers need to add to 30, I don't know that they're 15. If 15 and 15 will multiply to will add to 30, but it wouldn't multiply to 104. So it's got to be some value less than 15 and some value more than 15 that when multiplied together get us to a 104. So one thing that you could do, I don't think it would be fun. I don't even know what that was doing. Allow paste. Okay. I was just going to clear this out. But you could try 15 times 15. So that would be the case where x is equal to 0. Or maybe x is equal to 1, in which case you'd get 16 times 14. Maybe x is equal to 2. So 17 times 13. Maybe x is equal to 10. Right? So 25 times 5. Right? So you could trial and error your way to it. The problem that you'd run into is if it's a decimal value, find two numbers. It didn't say two whole numbers. You'd run into a problem there. All right, so that's an approach. It's probably not the most efficient approach, but it's doable. Instead, what we're going to do is distribute this out. I'm going to take my 15 by 15. 15 times 13 is 225. 15 times negative x is negative 15x. 15 plus times a positive x is positive 15x, and x times negative x is negative x squared. Right, these opposite terms are going to cancel out, and you're going to be left with just 225 minus x squared, and that's equal to 104. So then what I would do is subtract off the 225. I get negative x squared is equal to 104 minus 225, which is negative 121. Divide both sides by a negative 1. That'll get me x squared is equal to 121. Then I would take the square root. The square root of x squared is x. And because this is a Babylonian algorithm, we would only go with the positive. So x is equal to 11. But you could also make a case for a negative 11. All right, but we'll just keep it at that for now. I think that's what... Oh, they did the plus or minus this time. Okay. All right. I still stand by this. But what we could then do is take the 15... Oh, maybe they didn't. Oh, no, they just plugged it in. Okay. No, it's fine. To see what the actual numbers are, because remember, one of the numbers is 15 minus x, and the other is 15 plus x. All right, so 15 minus x, 15 plus x. So 15 minus 11 would be 4. And 15 plus 11 would be equal to 26. So 4 times 26 would give me the 104. So these would be my two numbers, 4 and 26. All right. So, like I said, I'll make up another example. Let's say we have... I want to make sure that it's something relatively clean. So let me do 13 times 17. All right, so two numbers that add to, so the sum is 30. Product is 221. All right, so I'm kind of working backwards from what I want the answer to be. All right, so I take that 30 divided by 2. That gets me a 15. So 15 plus x, 15 minus x is going to be equal to 221. We distribute this out, just like we did before. It's going to give the same result. 225 minus x squared is equal to 221. Then I would subtract off the 225, which gets me a negative x squared equals negative 4. Divide out the negative 1, and I get x squared is equal to 4, the square root of which would be 2. So x equals 2. So 15 plus x, 15 minus x, 15 plus 2 is 17. Oops. 15 minus 2 is 13. And so those would be my two numbers. All right. For the modern method, we assign variables, and then we use substitution and go from there. All right. So I will take you through that. I'll use my example this time, though. So again, it was a sum equals 30, product equals 221. If we let x equal the first number and y equal the second number, then the sum of those two values would be x plus y is equal to 30. The product would be x times y is equal to 221. All right. So the way we handle this is by taking one of the equations and solving for one of the variables so that I could replace the variable in my second equation with that new expression. So the most efficient way of doing that would be to solve my second equation, or my first equation, sorry, for y in terms of x. So y would be equal to 30 minus x. I can now replace the y in my other equation with what I now know it to be as 30 minus x. So x times 30 minus x equals 221. All right. Then I would distribute it out. So I'm going to take that x and multiply it by each term here. So 30x minus x squared equals 221. I'm going to subtract over the negative 2, or the 221. Actually, yeah, I'll subtract it over because we're using the modern method, so it's fine. All right, so in descending order, we don't have any like terms here. I'm going to write this as negative x squared plus 30x minus 221 equals 0. All right, so now if I'm using the modern quadratic formula, my a value is -1, my b value is 30, and my c value is -221. So saved it for later, just like I said. Oh, undo. So I'm going to plug in to this formula the relevant values. So 30, 30, -1, -1, -221. Pop it into my calculator. So I'll do a fraction, wipe out the a and s. So negative parentheses 30 minus the square root 30 squared minus 4 times -1 times -221 all over 2 times -1. All right, so that gets me a 17. And then do it again, changing the minus to a plus. And I get 13. X equals 13. All right, so those would be two values that satisfy the equation. So again, x is the first number, y is the second number. All right, so I'll take my x plus y equals 30, and I'll replace the x value with a 17. Oh, I highlighted the wrong thing. So 17 plus y equals 30. The y value that goes along with that would be 13. If I did the same thing by plugging in a 13 for x, I would get a 17 for y. All right, so I'll do that. X plus y equals 30, replacing the x with a 13. So long story short, we're going to get the same pairing of values. So here in this case, we would say x equals 17, y equals 13. And in this case, we get x equals 13, y equals 17. But ultimately, we got the pairing of values, 17 and 13, so it doesn't matter which one I call x and which one I call y. All right. So that confirms the answer we got before, and that's the modern method approach. All right. So example 2 is essentially the same thing, just going both ways. All right. Example 3 is a Babylonian area problem. All right. Oops, sorry, overshot the Mac. So the area of a square plus 6 times its side result is, or the result 40 required the side. All right, so that's the area problem. Now, if I draw out a square and I call one length x, then all the lengths are x. So it's saying the area of a square, area is equal to length times width. So x times x, which would be x squared. All right. The area of the square plus 6 times its side, 6x, results in a 40. All right. And you could use whatever method you want to solve this quadratic. If you want to use the Babylonian completing the square or quadratic formula, that's fine. Whatever method you prefer. All right. The hardest part in a lot of these cases is coming up with the equation needed to be solved. It's, beyond that, it's really dealer's choice. All right. So if you want to use completing the square, go for it. I used the quadratic formula for the last problem, so I'll complete the square this time. All right. So a little refresher on that anyway. So we leave a little space to complete the square. All right, we compute b over 2 squared, which is going to be 6 over 2 squared, which is a 9. So that gets plugged into the little gap here. On the left-hand side, that becomes x plus 3 squared, all right, because these two numbers always match, is equal to 49. And I'll take the square root. Left-hand side becomes x plus 3. Right-hand side is just the 7 because this is an area problem. Subtract the 3, and we get x equal to 4. It asked for us to find the side, and we got a result of 4, which is somewhere here. Yep. All right. And the second problem is essentially the same thing. So if you follow this approach, you'll get the right answer. And yeah, that's really it.